Hi all, and thank you for your interest in this work. My name is Amal Nanavati, and today I will be talking about our work modeling social interaction logic for one-to-many interactions. This is joint work with Malcolm Doering, Dražen Briščić, and Takayuki Kanda, and was done at Kyoto University and ATR International. As we are aware, service robots are being increasingly deployed in human spaces, such as stores, airports, restaurants, and nursing homes. As these images show, such deployments inevitably involve robots coming into contact with human groups. How these robots should handle such one-to-many interactions where there is one robot and multiple humans is an open question. At the same time, we are moving towards an Internet of Things world where cameras, microphones, and other internet-connected sensors will passively collect data about how humans interact with one another. This brings us to the core question of our research. Can we use this passively collected human-human data to learn one-to-one, one-to-many social interaction logic without explicit manual labeling? The HRI community has had many past works in both data-driven learning and multi-party interactions. However, these works typically focus on learning low-level components of a robotic system, such as gaze and turn-taking, and typically require someone to manually label and analyze the data for the robotic system. Past work from our lab has focused on learning the high-level interaction logic directly from human-human data without explicit manual labeling. This work builds on our past work in the Shopkeeper customer scenario, but extends it from a one-to-one to a one-to-many scenario. We began this work by collecting data in a makeshift camera shop. Our store had 3 cameras and a shopkeeper's counter. A network of 6 LiDAR sensors tracked participants as they moved around the store, and they used a headset and smartphone app to specify the start and end of their utterances. Each scenario had 1 shopkeeper and between 2 to 5 customers who were given various group assignments and objectives to increase the diversity of interactions. Overall, we collected 266 interactions, or 28.7 hours of data, across 51 participants. Our goal is to develop a system that takes in customer actions online and outputs how the shopkeeper should respond to them. Therefore, we must process our dataset into discrete customer and shopkeeper actions. During the data processing step, we convert our raw data, which consists of position and velocity per participant over time, as well as participants' recorded audio, into discrete movement and speech actions. Movement actions consist of participants moving from one discretized location to another, and speech actions consist of their vectorized utterances. The paper has more details about our data processing pipeline. As we mentioned, our main extension to past work involves moving from the one-to-one to the one-to-many scenario. Let us watch a video to understand the challenges in one-to-many interactions.
これでも風景も撮れるんですか？
はい、もちろんでございます。
これ安くていいかもしれないね。
In this scenario, the shopkeeper must determine that the utterance is not directed to her, but rather to another customer, and therefore she should not respond.
すいません。
In this scenario, the shopkeeper must balance between the needs of multiple customer groups when determining who to help. Let us keep watching.
ございましたらまたお呼びくださいませ。失礼いたします。
すいません。
はい、お待たせいたしました。
やっぱり景色が綺麗に撮れるのが一番欲しいので、これがいいかなと思うんですけど、お安くはなります。
In this scenario, customers are acting asynchronously, and the shopkeeper must be able to decide which customers to respond to and which to ignore. As we saw, one of the challenges in the one-to-many interactions is the asynchronicity of customer actions. Consider this sample interaction, where there is a group at the Canon and one at the Sony camera, but their actions are interspersed. One way of modeling the actions and reactions is in a global sequence, where every customer action has a shopkeeper reaction. In that case, consider the scenario before time 9. The global sequence would assume that the shopkeeper at time 9 is responding to the customer at time 8, when in reality, that action is just a byproduct of the asynchronicity. However, since the shopkeeper acted, we do know that they are responding to at least one customer. Therefore, instead of a global sequence, we use a per-customer sequence, where we separate actions based on the customer who performed them. Now, for each shopkeeper action, there are up to 5 candidate customer actions. However, we are guaranteed that at least one of them is the action that caused the shopkeeper reaction. This leads us to the following two-part neural network for predicting shopkeeper reactions to customer actions. The attention network takes in all recent customer actions as a per-customer sequence and outputs which one customer is most important for the shopkeeper to pay attention to. This is then passed on to a filter. If the customer who acted just now is not the one the shopkeeper should be paying attention to, their action gets filtered out. On the other hand, if the customer who acted is the one that the shopkeeper should pay attention to, that action is passed on to the interaction network as part of a global sequence that consists of only important actions. The interaction network then outputs how the shopkeeper should respond. However, we cannot train this network end-to-end, since the filter in between these two networks picks out one action from 5 contenders, which is not a differentiable function. In terms of training the network separately, we do have ground truth shopkeeper actions to train the interaction network, but we do not have the ground truth for who the shopkeeper should pay attention to, since we cannot get into the shopkeeper's head. Therefore, how do we get the ground truth attention labels to train the attention network? Although we don't have ground truth labels for who the shopkeeper was paying attention to, we know that the shopkeeper action should be most highly correlated with the customer that caused it. Therefore, if we consider the 5 contender customer actions that could have caused the shopkeeper reaction, only one should be highly correlated with the shopkeeper reaction. This brings us to the causal inference network, which is a helper network intended to learn this correlation. The causal inference network is only trained on the 5 contender actions at the time steps before the shopkeeper acts. It is similar to the combination of the interaction and attention networks, except we make it fully differentiable by replacing the argmax and filter with the differentiable gumbel softmax. This allows us to train it end-to-end. After training this network, the outputs of the gumbel softmax layer are used to create the labels for the attention network. In summary, we have a multi-step procedure for training our proposed system. First, we train the causal inference network, only on time steps before the shopkeeper acts, to learn the attention labels. We then extrapolate these attention labels to all time steps, which is explained in more detail in the paper. We then use those attention labels to train the attention network. Once that's trained, we filter out the unimportant customer actions and finally train the interaction network. We evaluated this network offline using hold one-out cross-validation on a balanced test set consisting of 5% of the data. We ran 2 evaluations, one to determine the correctness of the predicted shopkeeper actions and the other to determine the accuracy of the attention predictions. We used human coders for both evaluations and used McNemar's test to analyze statistical significance. This is a picture of the coding tool used. In our first evaluation, we wanted to determine whether the attention network improved the correctness of the predicted shopkeeper actions. Therefore, we compared 2 networks. The proposed system is the full network we presented earlier, and the without attention system is that system without its attention components. In other words, the interaction network of the without attention system takes in all customer actions, not just the important ones, and predicts shopkeeper reactions. We look at the correctness of predicted shopkeeper actions as determined by our human coders. Our results show that the proposed system is in fact better than the without attention system, with 77% correctness compared to 65.2%, which is a significant difference. In the second evaluation, we investigated whether using the causal inference network to learn attention labels improved attention accuracy. Again, we compared 2 systems. Our proposed system is the same system presented earlier, where the causal inference network learns the attention labels. Our without causal inference system, on the other hand, jointly learned the attention labels and shopkeeper actions by replacing the non-differentiable filter with the differentiable gumbel softmax layer. This time, we compare each system's predictions for which customer is important to pay attention to, compared with the human coder's predictions. Our results show that the proposed system is in fact better than the without causal inference system, with 90.7% attention accuracy compared to 61.5%, which is a significant difference. In conclusion, in this work, we developed a system to learn, without explicit manual labeling, how a shopkeeper should respond to multiple human customers. We then demonstrated the benefits of first learning who to respond to, the attention network, and then learning how to respond to them, the interaction network. Finally, we demonstrated the benefits of a novel technique to learn which customer likely caused shopkeeper actions. Thank you, and we're happy to take any questions via email.